So nothing in statistics is 100% sure. Any conclusion that we make, there will always be a degree of reliability attached to it. And that degree of reliability is a probability. So we are going to start studying Chapter 3, probability here. So as a neat opener here, there was this lottery in Massachusetts that changed its rules 1 week a month. And some MIT students were aware of this and found out that this particular lottery called Cash Windfall, that on those days when they sort of gave an extra bonus or doubled the payout, something akin to that, that they were almost guaranteed of a profit if they bought tickets on those days. So they, pooled all their money together and bought a bunch of tickets and continued to make profits. And then eventually they solicited investors and were buying, huge amounts of tickets, like $600,000 of tickets at a time, making 15 to 20% profit each time they did. So by the time they finished with the scheme, well, not really a scheme, but by the time they finished taking advantage of this opportunity to win in the system, they had actually made $8 million and were able to quit their side jobs that they were doing to try and get through school. So pretty cool. So it pays to know your probability. So let's get some definitions on the table here. So first of all, an experiment is the process of making an observation for a single outcome. Your sample point is the most basic experimental outcome that you can have. A sample space is a set of all possible outcomes. And then an event is some collection of the sample points. So that's sum of the outcomes. And then the probability of a sample point is the likelihood of that outcome, which is equivalent to the long-term relative frequency. And we'll write that probability like this. Probability E1, E is a sample point, 1 is the first sample point. Now some notes here for a sample space, and we'll use capital letter S to stand for sample space, which is the collection of your sample points, E1, E2, up to E sub n. The probability of each one of those sample points has to be between 0 and 1. 0 an impossible event, and 1 a certain event. And then if you add up the probabilities of all of those events here, probability V1, E2, all the way up to E sub n, you have to get 1 or 100%. And then if you have an event, a collection of outcomes, you sum the probabilities of the sample points that are in that event. Now, if these sample points are equally likely, then you can shortcut things a little bit here. And you can find the probability by finding the number of sample points in A divided by the total number of sample points in the sample space. So desired outcomes out of total outcomes. That only works if your sample points are equally likely. So let's look at an example here. So we roll a fair die. That's actually our experiment here. That's how we get our observation, is rolling a die. Example of a sample point would be roll a 1, for example. And we could call that outcome of rolling a 1 E1. Sample space, we'll use capital S for our sample space, set of all possible outcomes. So you could roll 1, 2, 3, 4, 5, or 6 on a normal die. And then an event would just be sum of the outcomes. So for example, we could let the event E be that you roll an odd number. And remember, events are collections, they're sets. So these are sets of sum of the outcomes. So the odd numbers would be 1, 3, 5. And then the probability of any of these sample points, since they're equally likely, probability of, we'll write it as E sub I, is all 1/6. So the probability of the event E, you add the probabilities of the sample points that are in the event. So 1/6 plus 1/6 plus 1/6. The shortcut is, since they're equally likely, the number of sample points in A is 3, and then divide by the number of sample points in the whole sample space, which is 6. So either way you get 3/6 or 1/2 or 0.5 or 50%. We can give our probabilities as percents, decimals, or fractions.